So I will be presenting the paper Self-Supervised Pre-Training for Nuclei Segmentation. It's presented in MICAI 2022 by Hawk and Huang. So firstly, I will outline my presentation. I will introduce the task, which the paper is trying to solve, then the motivation, contributions of the paper, the related work in this area, proposed approach, experiments, and quantitative and qualitative analysis, further strengths and weakness, and the conclusion of this. So moving on, firstly, the task of nuclear segmentation is a binary segmentation task where we try to predict the foreground where the nuclei is present from the background. So it's a digital histopathology image analysis task. There have been existing works using convolution neural network. However, there is a drawback with that approaches for the segmentation task that they have a limited receptive fields and they can't capture the global context. So recently there have been a few works with the transformers that come to the rescue. And however, the drawbacks of the transformer is that they are data hungry. So the motivation for this paper is like the most of the approaches they are fully supervised. However, the limitation is the domain gap that most of these approaches use the pre-trained weights. It's from the ImageNet, which has a morphological differences from this medical image domain dataset, which is not similar to natural image domain. So the solution with that came up was to use how we can use effectively the unlabeled data. So there have been some self-supervised learning approaches. However, the drawbacks of those are that they are using the pre-trained weights again from the natural images, which has the different texture, shape, appearance, and other characteristics from the medical image domain. So then the authors, they propose a threefold contribution in this work. Firstly, that they change the pre-trained data set. Instead of using the natural images, now they are using a large-scale annotated histology image dataset, which comes from the whole slide images. The second proposal is from in the self-supervised pre-training stage. They proposed a region-level triplet loss, which helps to differentiate foreground versus background features more efficiently. The third is the image scale prediction, which further boosts the knowledge of the nuclei size and shape at different magnification levels. So some related work in this domain, they're categorized into two parts. First is the self-supervised learning. So there has been two prior work using the self-supervised learning approach. First is the instance-aware self-supervised learning, which has the scale-wise triplet and count ranking as a proxy task. And the another work is using attention mechanism, which uses the scale classification to localize the nuclei. The second category of the later work is the supervised learning using vision transformers. So there has been some recent works. First is the trans unit, which does the multi-organ segmentation. Then SIT, which reconstruct the image from the corrupted image. The third is some learned relative distances between the patch embeddings. So the paper has used trans unit as their base architecture. So this is the whole proposed architecture. Um, this is from the trans unit, which is a combination of convolutional neural network and a transformer layer. The authors have proposed three losses over here, which I will go in detail in subsequent slides. The first is the region level triplet loss. The second is predictnet triplet loss, the predictness loss, and the third is the scale loss. So now first let's look into the main proposed novelty of the paper, which is the region level triplet loss. So the core idea of the triplet loss is to separate the features in the embedding space more effectively. In our case, the input is the background plus this non-background patches. And the intuition is that it will be able to predict the background using the 8 connected neighborhood spatial locations. So over here in the bottom two figures, you can see that we have to the network tries to predict whether it's a foreground or background using the features of these all spatial locations, neighborhood locations. So this is the foreground image. So this is like here the nucleus is present, whereas here the nucleus is not present. So this is a background patch where it's not a background patch. So they categorize it as a harder versus an easier task. So the second thing is the PredictNet. So PredictNet, it is a multi-layer perceptron, two-layer. So we concatenate all those 8 spatial patch embeddings layers and pass it through MLP layer to get a second feature vector, which is called Bij, and then we generate a hard matrix using the L1 distance between the previous between the spatial location versus the final MLP layer feature vector. They generate a hard matrix, and using this hard matrix, they do a triplet loss selection. So if the score is, so to categorize as a foreground as a background feature vector, they have two thresholds, and then using that threshold, they categorize the image features as foreground image features versus the background image features. So firstly, they have like an unscaled image, and so they have the foreground and the background. Then they have scaled image features, which has this again foreground and background features, and then they generate the triplets from this. So the triplet generation, it contains three components: anchor, positive, and negative. So the anchor, what they have used is an unscaled foreground feature vector, Fn. The positives comes from the scaled foreground feature vector, Fs, whereas the negatives, they come from the background scale versus scale versus or unscaled feature maps. So that was the first part where they did the region level triplet loss. The second part is the scale net architecture, where they use they try to predict the magnification level of the image. So scale loss, it predicts magnification level. It uses the size and the texture of the image. It further helps to localize nuclei. So they compute the attention map between the input and its segmentation map and feed this into a skill classification network. And this output a magnification level score. And they use this as a further constraint to better localize the nuclei shape in the segmentation map. Now, combining all those four losses, so three losses, the first loss was the predict net loss, where they have that L1 distance between the unscaled feature image and the scaled feature image. The second one is the triplet region loss, where they select the positives and negatives using this hard matrix to train that triplet. The third is the scale loss, which helps to uh, calculate the magnification of the image. And finally, the total objective of the self-supervised loss pre-training stage is the combination of all these three losses: the region triplet loss, predict net loss, and the scaling loss. And further, they just fine-tune the network on the downstream datasets. So coming to the experiments, firstly, the pre-training datasets that has been used, it's MonuSig WSI, which contains 30 images. Sorry for the typo. The image resolution is 1000 cross 1000, and then they extract a 512 cross 512 patches at 40 magnification level. So the number of total patches they get is around 178K. The fine-tuning data sets that they have used is first is TNBC, which has 50 number of images. The resolution is 512 or 512. The magnification is same 40x. They divide it in train validation test with a ratio of 80, 10, and 10. The second dataset that they use for the fine-tuning is the MonuSeg dataset, which MonuSeg, the downstream dataset, which contains the number of images around 30, but it is divided into 80% train and 20% val. And then there is a separate MonuSeg test, which contains 14 different test images. Now, going to the implementation details. So the model architecture that they have used for the feature extractor, it's the ResNet 50. And the second part is the skill classification network, which incorporates ResNet 34. And they have used a batch size of 16. The optimizer is SGD. Learning rate is 0.001, and retraining, they have to do it for 20 epochs, and fine-tuning is done for 80 epochs. And the evaluation metric that they show results on is the IOU and DICE score. So now, coming to the results, they show results on two datasets, TNBC and MonuStack datasets. So let's go through each of them in detail. So firstly, if we look into this part of the table, uh, so if we compare these, so these approaches are based on the convolution neural network. So they show that using they outperform this convolution neural network by a huge margin of like 3% on IOU and 2% on DICE score. Then they further show comparison with transformer-based architectures. So they're able to outperform all the transformer-based architecture uh, as well as some self-supervised learning based approaches. So SSL instance self-supervised learning approach, it has a backbone of ResNet. So they show comparison with ResNet versus including a VIT backbone, and they show that they outperform the previous approaches for both of the backbones and for both of the pre-training datasets where it's an ImageNet or it's a medical image domain dataset. Finally, they show some ablation study on their own proposed losses. So first they directly transfer, like without fine tuning, they evaluated on TNBC dataset. And so the scores is obviously relatively low since the source and target domain has some distribution gap. Then they show how the results are using the without the region triplet loss and without the scale loss. So if we compare between these two, we can see the gain of region triplet loss using that, um, because if we don't use the scale loss, then the performance is low. Whereas if we don't use the region loss, then the performance drops significantly lower. And finally, using all the losses, they outperform the previous things. And now comparing that across with another dataset, the MonuStack dataset downstream. So if we see first over here, this shows the comparison like the trans unit architecture. So see that a trans unit with their proposed region triplet loss, it also outperforms the previous trans unit architecture which was proposed in another paper. And then if we see the fine tuning, so we can see how the downstream dataset distribution impacts with the pre-training stage of source distribution dataset. So over here, the TNBC has a different distribution, whereas MonuSeg is the same dataset which has been pre-trained. So we can see there is a huge performance gap coming from like the supervised training to the self-supervised training stage, where the performance dropped like around by 20% over here, so from 65 to 48, where the performance dropped for only 3%. So that's why the retaining and the fine-tuning data distribution also matters. However, they show that they outperform on this data set as well compared to the previous approaches. Further, they show a qualitative analysis of this input image compared to the previous architectures. So they specifically show that these false positives, which is marked in blue, that they are able to remove those negatives in their paper. That further boosts their claims that this approach outperforms the previous approaches. Now, looking at the conclusion, so they have two-step proposal. First is the image, instead of using the ImageNet pre-training weights that has been used by the prior works, the paper utilizes a medical image domain dataset for pre-training. Um, they proposed a self-supervised region-level triplet loss in their work. Now, looking at the strength and weakness of the paper. So the strength is that they outperform the previous approaches, whether it's the supervised or the self-supervised on both the datasets. The use of region-level triplet loss with neighborhood path level features is patch level features is interesting. The weaknesses of the work is first is the ablation study. So in table we see that they have shown that they have three losses, but they have shown the results without using a region or a scale loss. but it doesn't show the contribution of each individual loss proposed in the work. There is a predict net loss as well in the work. So since it's the major novelty of the paper, I think that they should separate out each loss and then show the combination of each losses and how they perform. So that will quantify the gain of their proposed region level template loss. The second is the results. So the papers show scores only with the medical image domain dataset, but not pretending with the ImageNet dataset. So for some of the papers to compare with, like the previous papers which are based on CNN, which uses ImageNet architecture, for the fair comparison, the paper should also show the results on that medical image, like ImageNet pre-trained and fine-tuning on TNBC or MONUSIG dataset. Also, supervised scores using fine-tuning from WSI dataset is missing in the table. The writing is relatively a little bit poor because the notations that they have used in the paper, it's not declared first. It's sometimes it's mixed up with the methodology section and difficult to follow. The related works, it doesn't actually quantify how their work is related to the previous work or what's the difference from the previous work they have proposed. The conclusion, it's just poorly written. It's just a two sentence. They have proposed this self-supervised learning with the image medical dataset and region level template loss. So for me, I gave the rating of weak reject because the main thing is about the uh, proposal of this region level template loss. Since it's not it's difficult to see the gain where it comes from. Uh, and the gain is very minor. If you see in the table, compared to previous works, there is only 0.5% gain on the IU and the DICE score. So it's necessary to see which part of the loss actually is helping. Yeah, that's it.